Hello, everyone, and welcome to the first webinar in Sustainable Conservation's Recharging California webinar series. Thank you all for joining us today. We're thrilled to have Dr. Swain with us to kick off our fall webinar series. I'd like to give many thanks to our sponsors, Environmental Science Associates, Holland and Knight, and Spotswood Estate Vineyard and Winery for supporting our fall webinars and sharing Sustainable Conservation's vision of stewarding our natural resources for all Californians. I'm Ashley Boren, CEO of Sustainable Conservation, and for those of you who don't know us, Sustainable Conservation is a nonprofit that advances the collaborative stewardship of California's land, air, and water for the benefit of nature and people. That means that every day we're bringing together business, landowners, scientists, government, water agencies, nonprofits, and others to advance collaborative solutions to steward the natural resources we all depend on in ways that are just and make economic sense. So this fall, we'll be joined by climate and water experts to demystify climate change impacts in California and explain how we can better understand and prepare for our weather whiplash of drought and deluge. We'll highlight how groundwater recharge is vital to our climate adaptation toolkit, and we'll dive deep into Sustainable Conservation's collaborative efforts with communities and partners to scale resilience strategies like groundwater recharge, soil health practices, and ecosystem restoration. So this is how the next hour will go. In a few minutes, I'm going to introduce Dr. Daniel Swain. And Dr. Swain's going to start it off by sharing a few slides that'll give an overview of the increasing hydroclimate whiplash in California and why it's happening. Then I'll ask him a series of questions, after which I'll open it up to Q&A from all of you who are joining us. But you don't need to wait till the end of the hour to ask your question. Please go ahead at any time and enter the questions in the Q&A box that's at the bottom of your screen as they come to mind while Dr. Swain and I are talking. So, Dr. Daniel Swain is a climate scientist with concurrent appointments at UCLA's Institute for the Environment and the National Center for Atmospheric Research. He studies the changing character, causes, and impacts of extreme weather and climate events on a warming planet, with a particular focus on the physical processes leading to droughts, floods, and wildfires. He holds a PhD in Earth Systems Science from Stanford University and a BS in Atmospheric Science from the University of California, Davis. And he engages extensively with journalists and other partners, serving as a climate and weather science liaison to facilitate broadly accessible and accurate coverage surrounding climate change. He also authors the Weather West blog at weatherwest.com, which provides real-time perspectives on California and Western North American weather and climate. We're very fortunate to have Dr. Swain with us today to talk about how climate change is impacting California, and in particular, our water supply, and also how we can work to adapt to these changes. So now I'm going to turn it over to you, Dr. Swain, to share some of the introductory slides with us.
Well, thank you for that introduction, and also for the opportunity to have this conversation today. I think that it's a very timely one for a variety of reasons, and it's great to see so many folks who are participating in this interactive Q&A. I won't belabor the point too much. I'm not going to give a long talk, just a few slides to introduce the way I think about hydroclimate in a warming world, and as that relates specifically to California, because I think some of the considerations here are a little bit different than elsewhere, and also might be a little bit different than you may have heard in a variety of settings in recent years. And so I think there will be some familiar themes, maybe a couple of surprises, and then hopefully that will set the stage for the conversation to follow. So bear with me, I'm going to share my screen. You're going to see my whole screen for a moment, maybe my cluttered inbox. And now in a moment, you will see, hopefully, full screen, what I'm intending to put in front of you. All right, looks good. So just to quickly introduce the notion of what I mean when I say hydroclimate whiplash. the reason I focus on this notion of whiplash or volatility is because it's often the extremes at both ends of the hydroclimate spectrum that matter from a human and environmental impacts perspective. So it's not the years that are slightly wetter or slightly drier than average that are a big problem. It's the years at either end of the distribution, either the extremely dry years, the record-breaking drought years, as we've seen repeatedly over the past decade or so, but also the extremely wet years that cause problems from a human infrastructure perspective when we have widespread or severe flooding, which we've also experienced multiple times in the past 10 to 15 years. So these images, of course, are from a specific spot in Northern California, Lake Oroville and Oroville Dam, just illustrating the sequence that we've seen over a less than 10-year period, from record-breaking drought to extreme overabundance of water and then right back again. What I didn't include is that I could have added 2 additional photos to this since the last one up here in 2021, further illustrating that whiplash sequence that we've been experiencing in California in recent years. So without further ado, this is sort of how I think about climate change and hydroclimate in California, which is that it presents the possibility of both a wetter and a drier future, just at different times in different moments. And so if we think about only precipitation, we look at the seasonal scale, what we find is that there's not a lot of evidence that California's overall annual average precipitation will change dramatically, even in a much warmer world, which I think some folks have taken to mean that the hydroclimate itself isn't going to shift dramatically. But when we use those very same models to look at the most extremely wet and most extremely dry years, again, these are the same predictive tools that suggest that on average precipitation probably won't change very much. They suggest a dramatic shift towards especially extremely wet years, but also years that are even drier than the ones we saw historically. So you put those two things together, and what you get is a reality of little mean change in precipitation, but a large increase in what I call precipitation whiplash, this volatility of swings between increasingly wet and increasingly dry conditions. You can imagine if you add roughly equally at both ends of the distribution, your average doesn't change very much, but your experience in any given year can change quite substantially. And the reason for this, simplifying a bit, is essentially because of an effect that we've recently coined in a paper we currently have in review, the expanding atmospheric sponge effect. And the analogy works like this. Imagine that the atmosphere is essentially a kitchen sponge that can both absorb water that spills on your kitchen counter, say, but can also yield water if you wring it out over the sink, if it's saturated. And that in a warming climate, that sponge becomes progressively larger. So that expanding atmospheric sponge can not only hold more water in a warming climate, but can also potentially yield more water if wrung out. So of course, the wringing out analogy is precipitation, so heavy rain events, but the amount of water that it can hold relates to essentially the evaporation of water into the atmosphere. And what we know is that this relationship is actually exponential. So this is one of the truly nonlinear aspects of a warming climate. In other words, for a linear warming, which is roughly what we're seeing, that atmospheric sponge and its ability to both hold water on the one hand and yield water on the other is increasing at a rate of about 7% per degree centigrade of warming, or about 3 to 4% per degree Fahrenheit of warming. And so this increases the ceiling not only on how intense precipitation can become, this is the main reason why we see greater precipitation extremes, but also the atmospheric evaporative demand, which is essentially akin to the thirstiness of the atmosphere, its propensity to extract water back out of the landscape, out of plants, out of soil, out of bodies of water. And so in a warming climate, then, together, putting these two things in the same mix, the atmosphere becomes both thirstier when it's not raining, but also capable of much heavier downpours when conditions are favorable. And so on the wet side of things in California, this is mainly a matter of increasingly intense atmospheric river storms, these corridors of highly concentrated atmospheric water vapor that we've become quite familiar with over the past few decades. they're the main water delivery mechanism to California. So of course, when they're in mild to moderate form, they're primarily beneficial because they essentially bring most of the water that California is going to get in any given year. So they're important from an ecological perspective, they're important from a water supply perspective, but they're also responsible for the vast majority of California floods. And what we expect is that in a warming climate, we will preferentially see more extreme atmospheric rivers, ones that trend towards the intense or even unprecedented end of the intensity scale and become capable primarily of hazards more often than benefits. So there will, of course, still be a mix of the two, but we see a shift from more mild to moderate events on average to more extreme ones in winter. So more intense winter storms when they do occur, but not necessarily more of them. And this likely, in some places in California, will bring a very large increase in the peak runoff. This is particularly true in the San Joaquin and Sacramento River watersheds. Of course, those are the watersheds that have their headwaters up in the high mountains in the Sierra Nevada. So it's not only a question of increasingly intense precipitation there, but uh, also a function of the fact that it is simply warmer. So you have to go higher and higher up the mountain to experience snow rather than rain, which means that more of that water that's falling with increasing intensity is falling as liquid rain rather than snow. And so it's immediately contributing to flows in rivers and streams, in other words, runoff, rather than accumulating as snowpack to melt weeks or months later on. And so that combination really suggests that in certain places that are historically received a lot of snowfall in the mountains, but that will also experience large increases in precipitation intensity, we'll see very large increases in the most extreme runoff in a warming climate. And then to close the loop, I just wanted to emphasize what this looks like on the dry side of the spectrum. If we look at precipitation in the American Southwest, as you see up on the upper left, and the plot, quite frankly, looks very similar just for California, we don't see a long-term decrease. But we sure do see a long-term increase in temperature over that same period over the past century or so. And we also see a sharp increase in the frequency and severity of drought. What this is telling us is that it's not primarily a question of decreasing precipitation on average, but instead a statement that the same amount of rain and snow as we used to get just doesn't go as far as it used to, because we're seeing more precipitation concentrated into fewer days with more intense but potentially less storms, with, of course, less snowpack, as I mentioned, but stronger evaporative demand. That's the expanding atmospheric sponge I mentioned earlier. And that's largely because droughts themselves used to be hot or cold. It could be unusually cool with low precipitation or unusually warm with low precipitation. But today, virtually all droughts in the Southwest and California are hot droughts. So that evaporative component is amplifying all other droughts that would have occurred. And this is, by the way, the primary reason why wildfires are linked to climate change, which is to say the expanding atmospheric sponge dries out the landscape increasingly during the driest periods, resulting in more flammable vegetation and wildfires that can behave more aggressively. So that's about all I've got for you right now. Hopefully that provides some context and some fodder for the conversation to come. And you can find me on all sorts of social media outlets above. So I'm going to stop sharing my screen so we can begin the conversation.
That was an excellent overview. Thanks so much, Daniel. You know what I think you've just shown is kind of validates what I think a lot of Californians have been thinking, which is the weather seems to be changing. It seems to be getting more extreme. We know that California has the most volatile weather in the United States, but I think what you just showed us is the reasons that we're not crazy, that the weather is in fact getting more volatile already. Is that the case?
Yeah, I think the one challenge in detecting the signal of increased hydroclimate whiplash, if you will, in a place like California is precisely because California is already and has long been a place that experiences a high degree of hydroclimate variability. So on the one hand, it's an enhanced flavor of something that California and its peoples and its ecosystems are already used to a certain extent. It's what California's geography is shaped by. It's what its ecosystems are adapted to up to a point. But yes, I think we're right now today, right at the point where we're starting to be able to detect some of these changes, even relative to the relatively noisy historical signal. And so I think we're there. We're right on the cusp. And the last decade in California, I would say, or the last 10 to 15 years, as I noted in the opening, is, I think, if not proof that we're already there in the long run, certainly representative of where things are headed. And so the past decade or so has been a taste in the sense that we've seen both record-breaking drought twice in the past 12 or 13 years. So not just once, but twice on two separate occasions, as well as in the intervening years, the largest and most destructive and fastest spreading and most intense wildfires in modern history in California, and some of the most extreme precipitation events. Fortunately, not the most severe flood events due to a series of essentially fortuitous,
Mhm.
really good luck more than anything else. But we've gotten a taste on both ends of the spectrum, and I think that's increasingly we're going to see decades that are a little more drought flavored or flood flavored, if you will, than others. And I think we just experienced a decade that was more on the drought side of things. But at some point, we're going to see a decade where we experience more flood than drought. And I think that may still catch some folks by surprise. And so I think once we get to that point, we will have fully entered this sort of this new era.
Yeah, you speak about the fact we were fortuitous. I think you're referring to 2023,
Exactly.
which we did actually experience some pretty severe flooding in certain areas, definitely loss of property and life. But my understanding, and maybe you can validate this, is that we were very fortunate it wasn't warmer and that the snowpack really stayed for quite a long time, or the flooding might have been much worse.
Yeah, you have it exactly right. There were two things that we got very lucky about, one of which is exactly what you mentioned, and the other is maybe a little bit underappreciated. The first is that the sequencing of events, the storms managed to space themselves out
Hmm.
just enough that they didn't quite build off of each other in the same way in terms of the flood risk that would have happened if they had occurred just a couple of days closer together. So if we had had that same amount of water that we got in winter 2022, 2023, but over maybe even a week or two shorter period, that would have been a more serious situation. But I think the big thing that saved California, relatively speaking to what it could have been in 2023, was especially that late winter and early spring coolness. It was, by modern contemporary standards, an extraordinarily cold winter. Remarkably, a winter that would have been not that remarkably cold 100 years ago, and yet was still the coldest winter in over 40 years. We got really lucky because, as you say, had there been an earlier, sharper snowmelt peak, or if some of that snow had melted to a greater extent while it was still raining, the San Joaquin Basin in particular could have seen widespread, severe, and even catastrophic flooding. And that, I think, was something that the state was preparing for, steeling itself for. And while there was, as you say, destructive, damaging, and even deadly flooding in a few cases, it was not the big one, if you will, that eventually we will see in the San Joaquin Basin. And so we did indeed. We threaded that needle in a way that was actually implausible. And by the way, the estimate is that we will probably never see a winter as cold as 2022,
Hmm.
2023 again in our lifetime. So
Wow.
it's unlikely that we'll be that lucky again the next time we have a very wet winter.
One other factor I remember hearing also was we were in a way fortunate after having that intense drought was our reservoirs were quite empty. So there was a lot of room to collect that early storm runoff that happened, that if they had been full would not have been possible.
Yeah, that's also a very good point, is that we went into that winter on the heels of another big drought, and so reservoir levels were quite low. There was a lot of headroom, at least for those initial storms, so we didn't start with flood risk right away. We had that ability to buffer, and that's an important point, looking forward to the future, is that most of California's major rivers, especially, on the western slopes of the Sierra Nevada, which are upstream of the Sacramento and San Joaquin basins, and therefore all drains to the Delta, so affects everyone downstream of that. Uh, most of them are dammed, and most of them have reservoirs of different sizes on them, most of which are dual purpose. We think about reservoirs most often from a water storage perspective, but from a flood management perspective, not all reservoirs are designed primarily for flood control, but all of them have at least a de facto purpose of buffering flows. So in a natural river system, an unmanaged river system, the flow is what the flow is based on what the weather is doing, and what the upstream watersheds are how they're behaving. But with these dams, you can, if there is room to do so, regulate the flows quite dramatically downstream of dams. If you have an empty reservoir at the beginning of a big storm, in some cases, you could theoretically decide not to release water, and all of that water upstream would stay in the reservoir. Now, typically that's not how they're managed for a variety of practical reasons, but we got very lucky with that. And I think that is one important lesson, that's where things almost went sideways in the San Joaquin Basin with Isabella Dam. The ability to, by the end of the season, to spill water was right up at the top of the level of what these structures were designed for, and slightly exceeded it for brief periods, but not for long periods and not by a wide margin. And had there been a stronger snowmelt pulse that season, we would have gone well above the capacity of that infrastructure.
But we'll come back to reservoirs and the possibility of reoperating as one of the tools for adapting. But you kind of hinted at where we know, so now kind of where we are now, you've hinted at where we might be going in the future. I guess, how quickly might we see some of these future impacts, and what might they look like?
Yeah, I mean, this is the tricky part, and I did allude to this earlier with this signal to noise ratio challenge of, can we detect this scientifically with high confidence in a place that already had a lot of variability to begin with. One place where we can definitely unambiguously detect things is we know that the snow line is creeping up the mountain, or maybe at a slow jog rather than creeping at this point. We're seeing less snowpack on average in the mountains than we used to, and a higher mean freezing line than we used to. Interestingly, we still get these really big snow years and individual big snowstorms. So there's a clear decrease in the average snowfalls, but not a clear decrease in the most extreme snowfalls. And so that's another aspect of, and sort of an interesting high mountain snow whiplash thing. Of course, we're detecting these large, these strong and increasingly so increases in temperature itself. That's maybe the most obvious one. But when it comes to the hydroclimate, I think that we clearly have seen an increase in the frequency and severity of drought. So we know that that's absolutely already underway, unambiguously, and substantially exacerbated by the climate change that's already occurred. I think the trickiest part is when it comes to precipitation itself, partly because, frankly, we don't have great historical records for precipitation. We did not do a good job of measuring it, and we still don't always. And so it can be tricky. But here's the way I think about it. That expanding atmospheric sponge effect, that 7% per degree centigrade or 3 or 4% per degree Celsius that I mentioned, that is not, the product of some speculative science, or even necessarily the product of these climate models that we often talk about and that I've invoked in some of the other parts of this conversation. This is the product of quite basic thermodynamics that goes back into the mid 1800s. The Clausius-Clapeyron relation is something that is the product of science done essentially by two scientists well over a century ago, well before there was any kind of computer modeling available. This is a fairly basic aspect of atmospheric physics and thermodynamics. The fact that the sponginess of the atmosphere, if you will, it goes up by about that amount when it gets warmer. And we know in California that we're about 2.5 to 3 degrees Fahrenheit warmer than we were a century ago. So if we just put two and two together, we're 2.5 to 3 degrees Fahrenheit warmer, and the increase in the sponginess, if you will, of the atmosphere, or the size of the atmospheric sponge is about 3 to 4%. Multiply it by about 2.5 to 3 degrees. That is sort of my baseline expectation for the degree to which this whiplash, these swings, the climate change component that we should expect to see right now. Now, of course, there's also natural variations in climate that are superimposed on top of this, and that can mean that it takes a few extra decades to make the signal really clear. But frankly, that's sort of my baseline estimate. So, conservatively take about 2.5 and multiply it by 3, or if you want to go for the higher number, take about 4 and multiplied by 3, and we're up above 10%. So that's actually quite substantial
Yeah.
when you're talking about extreme events. Take the worst flood you've seen, make it 10% larger in volume, take the worst drought and make it 10% more severe, plus 10 plus percent, because of course there are cascading impacts from these things. Human and natural systems have nonlinear thresholds. A tree in the forest or the forest itself has a certain threshold of water stress beyond which the trees can't survive. A levee or a dam is built to a particular height. You can go right up to that height and everything is okay, and you go slightly above that height and things are not. In fact, we almost learned that lesson quite dramatically with the Oroville Dam crisis back in 2017. We got right up to that point and just above it, and we're very lucky that the storms weren't 10% more severe or 10% warmer, because that would have gone from being a crisis potentially to a real catastrophe. So that's a good example, I think, of how even our managed systems are sensitive to even a 5 or 10 or 20% shift in things like this.
And I guess it's very difficult to predict kind of over what time span we might see this, because that all depends, of course, on how the planet, or how we uh, how successful we are in trying to keep greenhouse gas emissions down. But do you have any comment you want to make on just sort of timing of how we might experience some of these more dramatic increases?
Yeah, I mean, really, it could happen at any time. I mean, it could be this winter, it could be 35, 40 years from now when we see, the big one in terms of the next really large catastrophic flood in California, or the next drought that surpasses the one that the record-breaking ones we've seen in recent years. The likelihood does go up somewhat with each passing year by a small amount, and so therefore, with each passing decade, the likelihood is going up tangibly. The risks today are quite different than they were in the year 2000. We're living in the future in that sense. We're getting close to a quarter century beyond the year 2000, as hard as that is to believe. So we're essentially a quarter of the way through the 21st century. And so I think in a lot of our minds, the 21st century is still this distant future thing. And we're in the middle of it now. We're in the future in a lot of the futures that were predicted 20, 30 years ago. And so any given year, it's often difficult to say. We still have that natural variability. We still have natural processes like El Nino and La Nina in the Pacific Ocean that modulate the risk from year to year somewhat, and other natural variations that we don't fully understand or have the ability to predict from year to year. But there is some indication, generally speaking, that the last 10 to 20 years or so was dominated in the Southwest and in California by a period of perhaps unlikely dry conditions, in the sense that natural variations may have masked the erstwhile increase in extreme precipitation and flood risk during this period. And so we may have gotten, in a certain sense, artificially lucky on the flood side. Now, that may have meant that we got artificially unlucky to a certain extent on the drought and wildfire side. So we may not see it, a decade coming up that's quite as severe as the last one from a drought and fire perspective. But what we may see as that happens is that we actually start to see more events on the flood side of things. And, my point is that I don't think we're going to be able to predict in advance whether a particular decade is more drought or flood focused, probably both to a certain extent in every decade moving forward. But that in general, the likelihood of both of these things increases, that's not a contradiction in terms, is that there will likely be decades that feature both in the same 10-year period. And years like this one, for example, where we feature certain aspects of both even in the same year. So, of course, California is not experiencing a severe drought right now, but we have seen a pretty serious wildfire season already this year, and it's likely to amplify with the current heat wave. That follows 2 consecutive wet years in some parts of California. In fact, in coastal California, 2 consecutive very wet years. And yet we're seeing certain aspects of fire season this year that are really remarkable. And part of the reason for that is this whiplash sequencing, because in some ways, from a wildfire perspective, for example, the worst climate for wildfire isn't just one that gets perpetually drier, because then, of course, you have a big spike initially in wildfire activity, but eventually you see so much fire that you start to transform the ecosystems in the landscape into ones that have less and less vegetation
Mhm.
and therefore less and less fuels for the fire. But in this reality, which is the one I think that's more analogous to what we're going to see moving forward, we see alternating sequences of extreme drought and extreme wildfires with very wet conditions, and that allows that vegetation to regrow. So in some ways, it's good news because it means that unlike I think some folks who have sort of had this view that California is just going to shrivel up like a raisin and never see rain again, there were people who were really worried about this during some of the worst droughts of the last decade. That doesn't really seem to be what our future will likely hold. There will be these episodic bursts where we get a ton of water, ton of rain, and less snow, but still some snow up in the mountains. A lot of water up there during the wet season. The question is, what are the implications if it becomes an increasingly inconvenient and potentially dangerous individually large surges, whether it's increasingly large individual storms or wetter individual winters at the expense of a more nicely, evenly distributed process over years and seasons?
So that let's move to adaptation and what we do to prepare for this future that we seem to already be in or are certainly headed for. So I've often heard the phrase that, California's got 19th century policies, 20th century infrastructure, and 21st century, conditions. So kind of how are we faring, and what does the state need to do to help prepare for this future?
Yeah, and I generally agree with that. I actually don't know where that quote originated, but
I
I've
don't
heard it
either.
from so many people over so many years in the California water world. Ironically, I think that the statement may have even originally been made before we entered the 21st century, saying that conditions aren't what they used to be. But of course, now that we're, as I mentioned, a quarter of the way through the 21st century, we are truly there. And yet, and I think that that actually speaks to another aspect of this, which is that I think that's true. And to it, I would even add the fact that the 21st century isn't a monolith in itself. The second quarter of the 21st century and the third quarter of the 21st century are going to look a lot different even than the last 20, 25 years have. And so it's a perpetually moving target in that sense. And yet most of our infrastructure hasn't changed still. And so to the
Mhm.
extent that our infrastructure was built using old techniques and designs for a climate that didn't exist when it was built, it certainly is misaligned with the climate today, and it will be even more misaligned with the climate 10, 20, 30, 40 years from now. And so that's another piece to this. But I think the challenge is that this is broadly true. This is not really a California specific problem. It's particularly acute here because we do have such a very advanced and both simultaneously advanced and also kind of stuck in the past, but maybe the better term is comprehensive and very important water infrastructure. So it's highly managed. There is a lot of infrastructure. Some of it is, they're physically large, technologically complex, and big ticket in the sense that they were expensive to build and would be even more expensive to replace or maintain today. There's a lot riding on this. A lot of the state's economy, a lot of the state's natural ecosystems are affected for better or for worse by this infrastructure, and in ways that aren't fixed. How we operate that infrastructure dictates the, the benefit to cost ratio, both for human systems and natural systems. And the challenge is that, as I mentioned, it takes a long time, a lot of money, and a lot of effort to build new big infrastructure projects. And in California, most of the major waterways already have large infrastructure projects that were built decades, in some cases, many decades ago. And I think sometimes folks forget that we are, for better or for worse, largely stuck with the legacy of what we have. And I think California, from a human population side, is better for having that infrastructure because otherwise, for example, we would have had multiple catastrophic floods in the 20th and 21st centuries. We would have had
Mhm.
droughts that resulted in food shortages and cities running out of water. And we have not seen that with some local exceptions. We haven't seen big cities run out of water partly because we have this infrastructure. And yet, at the same time, there are, there's growing evidence. This was obvious to some folks for a long time, but I think has become better quantified in the scientific literature in the last decade or so, that there are also a lot of harms ecologically, in terms of environmental justice from these projects in terms of who and what they protect at the expense of other entities and people that they don't, or may even make certain things worse for them by virtue of protecting these other assets or people or communities. And so I think that it's a complicated question because this is really where the science meets society, meets non-stationarity, meets policy. And everyone knows that the California water world is almost impossibly complicated to describe to somebody who has no primer in it. But I think this is really the challenge is despite all of that complexity and all of the practical considerations and limitations that exist, we can't ignore the fact that the water systems we have were built using old technologies for a climate that no longer exists already and that certainly isn't going to exist a few decades from now.
Yeah. So we're at Sustainable Conservation, we're big believers in green infrastructure. We definitely recognize, the benefits that California has accrued from the water infrastructure it's built. It's probably some of the most incredible water infrastructure in the world. But as you said, it has had its harms and it's not prepared for the future. What role do you think green infrastructure can play? So, floodplains, letting water, these flood events spread out, slow down and sink into aquifers, for instance, can play as part of the solution. And what does it take to get that to a scale where it actually really can have a significant impact?
I mean, I think it could plausibly play a very large and actually underappreciated, I think, widely underappreciated role in both mitigating risks. So even if we only think about the risk mitigation, the cost side of things in terms of harm to human systems, places, people's homes, infrastructure, critical infrastructure, things like that, as well, of course, as the benefits that they intrinsically would provide in other ways in terms of restoring ecosystems and resulting in having more accessible and broader outdoor spaces for people to enjoy too. I think that this is something that is actually quite commensurate with the kinds of whiplash changes that I think are already starting to unfold and that we will especially see unfold in the coming decades, which is because if we were to see a climate that just got dramatically drier, and we had to deal solely with extreme water scarcity all the time, or if we were to have a climate that got monotonically wetter and we had to deal solely with a big increase in flood risk, then this might be a little bit less true. But in this reality, where the average precipitation may not shift all that much, but it may become much more concentrated into wet years and wet seasons and wet individual storms at the expense of virtually everything else, that tells us that technologically speaking, we probably cannot build our way out of this with ever more, concrete, in the sense that, flood walls and levees and flood protection is, I think, very helpful up to a point.
Mhm.
And there is always a point beyond which it no longer protects you. In fact, can even give a false sense of security on the flood side of things. Likewise, during a severe drought, the reservoirs we have, the storage systems we have, give us an enormous capacity to buffer against even historically unprecedented droughts, at least so far. We tested that this past decade, and we didn't pass all of the tests, but we passed a lot of them, at least in terms of major cities and the economy. And yet there is still the potential for longer and more severe droughts that actually surpass that adaptive capacity that we have with the system. And the thing is, building ever larger dams or ever higher flood walls is very expensive. You have sort of exponentially increasing negative externalities because most of the time you don't need them. And so you're stuck with this ugly, inflexible, and in some cases, actively harmful infrastructure when it's not being used to mitigate extremes that are increasing, but still aren't happening most of the time, statistically speaking. Whereas on the other side of things, what you have potentially are interventions that you actually benefit from when you're not leveraging them from a risk management perspective. So, expanded floodplains become habitats and parkland when you're not using them in a flood absorbing capacity, and sometimes even when you are. And so I think what really comes out of this is that how do you co-manage the risks of drought and flood? And in a lot of ways, it is, to use a term of art, letting the water do its thing to a certain extent within some controlled bounds. Obviously, you don't want to remove all the levees and all the flood control systems, because then you'd have, Sacramento would flood every 5 or 6 years, for example. But on the other hand, there are a lot of opportunities to set back those levees so that you have a wider floodplain in which rivers can meander, to restore floodplains. Maybe there are some levees that we don't need that are either, they're already full of holes anyway and aren't really secure or stable. Why don't we just get rid of them entirely? Why don't we restore these places, these wetlands, or these ephemeral wetlands or floodplains that might actually still be dry most of the time, but during big flood events could become vast floodplains. And there are some examples of this. This is essentially what the YOLO bypass is
Mhm.
in the Central Valley, which is this quite impressively large swath, 20 miles wide swath of land between Davis and Sacramento, that when the Sacramento River is running high, the weirs on the river are opened and it is allowed to flood. And so that is why when you drive between Davis and Sacramento, you're driving Interstate 80 on this long causeway bridge, because every few years or so, all of the land underneath that bridge is covered with at least a few feet of water. And that's why you don't see subdivisions there. It's why there is some farming going
Mhm.
on there, but it's farming that can accommodate, it's going to be underwater, episodically. So that's been a very successful intervention in taking the pressure off of the levees in Sacramento. It's actually become a fairly important piece of the Pacific Flyway,
Mhm.
when it pops up, pop-up wetlands, if you will.
Mhm.
Um, but that's one example, and I think that there are a lot of other opportunities to do that at different scales. Some of these are small scale projects, but I think what we may be missing, and this is sort of what I'm trying to get at here, is that we're underestimating the degree to which the flood risk is going to increase in a warming climate, I think, in a lot of places in California. And so I think we need to be thinking big about where else can we have major river bypass systems, large scale floodplain restoration, easements maybe on fairly large swaths of agricultural land that maybe it doesn't flood every year, maybe it doesn't even flood every 5 years, but in the really big events, can we put agreements into place and retool the downstream infrastructure to say, these are the places that are going to get water first? Because we know the water is going to have to go somewhere. We don't want it to be downtown Sacramento. So where else can it go? And rather than making those decisions at the last minute, in a way that probably result in suboptimal outcomes, how do we put that into place in advance? Because we'll improve some of the ecosystem benefits in the meantime, will reduce flood damages in the future, and can there even be conjunctive? Speaking of co-managing the risks of drought and flood, one of the challenges in the Central Valley is this massive overpumping of groundwater during dry periods, primarily for agricultural purposes. But if we're going to have overabundance of water in some years, is there a way to ensure that more of that water goes back underground into these aquifers? Now, you can't just spread water everywhere and assume it's going to percolate nicely. There's all sorts of challenges in terms of what the geology looks like. Some places the water doesn't want to percolate. Some cases there's pollution that you don't necessarily want to introduce into aquifers. But generally speaking, there are a lot more opportunities to do floodmar, so flood managed aquifer recharge, essentially taking these flood flow pulses, combining them with expansion of floodplains and strategic easements on agricultural lands or things like that, saying, okay, we're going to use this water. You're going to mitigate the flood risk by shunting this water somewhere else. And also, by the way, that is going to percolate into these groundwater aquifers and give us a better water bank to draw upon the next time there's a big drought. At the same time, this can reduce the pressure on upstream reservoirs, because water managers may feel more comfortable about releasing larger amounts of water in advance if they know that some of it is going to be effectively banked underground, which gives you wider flood margins and then better margins for preparing for the next drought to come. So that's just a big picture example of how the land can be managed differently to accommodate this. But I'll pause for a moment. There's also other things in terms of
Yeah, I think
operating
there's a
infrastructure.
lot of opportunity there. And in fact, I think in 2023, we saw a lot of progress. There's a lot more opportunity for sure to be able to do this at scale, but the Public Policy Institute of California did do a report on how much water was able to be diverted in that big water year 2023 and to be recharged into groundwater. And I think it was a 17% increase over 2017. And farmers really stepping up to the ones that had good soils for percolating, allowing their lands to accept floodwater to do exactly what you're saying. So there's progress. So I know I could talk to you all day, keep asking you questions, but I see quite a few questions in the Q&A. So I'm going to move to those so that we get at least some of the audience questions together. Okay, so the first one is the state's guiding document, California's water supply strategy, adapting to a hotter, drier future. And the state policy seems to focus on the question of drier. What can we do to change this narrative and policy approach to focus on the and wetter as well?
Yes, well, I mean that has been a big part of the message that that I've been conveying to folks, the state government, at the level of the governor's office, Department of Water Resources, Cal OES, and at regional levels as well as through NGOs. I think I think you're right that this has been historically more of a focus of the risks on the dry side. And I think the great irony there, in some ways, is that there's actually more evidence for very large increases in flood risk than there are for very large increases in drought risk. Now, as I mentioned, I do think that both are going to increase and have already increased. But the drought risk is mainly in California being driven by the dryness, the dry side of that atmospheric sponge. So rather than a large decrease in precipitation, it's mainly on the increased evaporation side. So in other words, we're still getting that water falling from the sky, but it's more rapidly re-entering the sky. That's kind of why we have this concern over dryness. And so I do think that we will see a lot more years of water scarcity, but not so much because of the increase in the low precipitation years, but more on the other side. And yet, I think that on the wet side, that is more of a slam dunk kind of problem that we'll be dealing with. And historically, it's been underemphasized, partly because we got lucky, I think, in a certain sense in the 20th century. Generally, we're talking about 2023 being lucky, but also we didn't have a really big catastrophic statewide flood event in the 20th century compared to what we know is possible in the geologic record. This is something we've worked on in a project called ArcStorm 2.0 that you can Google. We have some papers on that, but I think that there has been a little bit of progress. In fact, speaking of the Public Policy Institute of California, they just put out an interesting article that I was reading this morning on how, despite budget cuts this year, the one climate and water related line item that actually saw a slight increase in spending, although it's still a relatively small amount of spending overall, was flood and flood protection related work. That was not true of expenditures on the dry side or others. So part of that is probably motivated by just how extremely wet 2023 was and how close we came to a much worse outcome then. But I would like to think that that's also because there's been a little bit of a messaging shift so that the policy is a little more aligned with what the science says about large increases. And to their credit, I know that DWR has, in its most recent version of its future stress testing, implemented a different and I think much better methodology where there's not necessarily an assumption about a large change in average precipitation, which I think has long been appropriate, but they do explicitly include about a 7% per degree centigrade increase in the most extreme precipitation events, even as things get warmer. And so I do think that is essentially the right way to be going about it moving forward.
That all sounds very good. Here's another question. The diurnal change in temperatures in the Sierra foothills appears to be narrowing as average evening lows increase faster than average day highs. This narrowing seems to be occurring faster than the narrowing occurring in the San Joaquin and Sacramento basins. Do you agree? And if so, do you see it continuing?
Well, that's an interesting question. I don't. It's certainly plausible. We've seen a lot of years where the overnight minimum temperatures have been really, really warm. In fact, this summer, being perhaps the most dramatic example of this, I believe in that thermal belt in the foothills, this was probably the summer with the least diurnal variation. That would be so. Certainly, the recent data point is consistent with that. What is interesting generally is that in a lot of places, overnight minimum temperatures are in fact warming faster than daytime high temperatures over much of the world. So this is actually a signature that we see in a warming climate, that nights are warming faster than daytimes. I can foresee some physical reasons. It's an interesting science question why this might be amplified in the thermal belt. So when I say thermal belt, I mean the sort of the foothill elevations between about 2,000 and 4,000 feet elevation. It varies a bit throughout California, especially in the foothills ringing the Central Valley. That is because often there will be a temperature inversion there during heat waves in summer, meaning that temperatures actually increase with height instead of decreasing with height, as is more common at night. And so the valley
Hmm.
might get down to 65, 70 degrees, which is a pretty decent overnight recovery, but you might still be 80, 85, and even 90 degrees at 3 o'clock in the morning at 3,000 feet elevation. We've seen a lot of heat waves this year that have done that. That's a little more true in summer, in the warm season, than in winter, but it's a plausible hypothesis. And I think this is one reason, by the way, we've seen such rapid loss of median snowpack at lower elevations. We
Hmm.
don't see that loss so much up at 7, 8, 9,000 feet. Of course, there's a lot less land in California up at 8,000 feet than there is at 5 or 4,000 feet. So as you'd expect, that warming at 4 and 5,000 feet is where we've seen a lot of drought, wildfire, and snowpack reduction
Hmm.
related impacts. So I think we are seeing elements of that. But I don't know with 100% certainty if that's a trend that might continue or if it might be a little more equal opportunity warming in different spots.
Okay, this is a clarification question. So just for clarification on hydroclimate into the future, the models project less storm events overall, but an increasing frequency of extreme events in those storm events that do occur. However, the question is whether these extreme events are just longer in duration or just more intense and shorter in duration. You can clarify that?
Yeah, so the strongest evidence is that the intensity of the events increases. So that's the number one thing that we find is that the intensity of precipitation increases for multi-day storms by something on the order, and this, by the way, varies considerably where you are in California. It's centered on about 7% per degree centigrade or 3 or 4% per degree Fahrenheit, but there are some places where it's a lot higher and some places where it's a bit lower. But it is mainly that precipitation intensity that increases. And what is interesting and somewhat concerning is that for the shorter duration events, the intensity increase is actually quite a bit larger. So if we talk about 1, 2, 3 day storm accumulations, how much water falls from a particular atmospheric river or pair of atmospheric rivers, that's close to that 7% per degree centigrade of warming rate. But if we're talking about the most intense hour of the most intense storm of the year, that increases faster, more on the order of 10 to 15% per degree centigrade. So that raises concerns over flash flooding, even more so than river flooding, or of debris flows and landslides as opposed to river flooding. And it also suggests that urban flooding, storm drain, cities that need to pump water out, like Sacramento, could have some real issues with that. So the shorter the duration, the larger the expected increase in precipitation intensity. I don't think there's evidence that storms become longer necessarily. In fact, there's even a little bit of evidence that maybe they're even a little bit shorter. But the increase in the intensity of those storms will still lead to higher daily and multi-day precipitation totals, even if the storms are a little bit shorter. There's a bit of a tongue twister. They'll be so much more intense that that essentially outweighs the effect, and that's particularly true for extreme downpours. And just one brief aside, I know we're running short on time, but we've seen a lot of these one-off individual, very intense hour of precipitation storms in recent years. In fact, just this past winter, we saw extreme rates of rainfall and flash flood events in multiple California urban areas that were not associated with major large-scale storms. These were like localized thunderstorm downpours that dropped anywhere from about an inch and a half to 4 inches of rain in an hour
Mm.
in places like Long Beach, San Diego, uh, the San Francisco as well. So these are three major places in the past year that saw urban flash flooding from extremely intense, even record-breaking short duration precipitation events. So just to give you a sense of, it's a little bit complicated since it varies over a function of time scale, but generally, yes, and storms themselves intensify, greater intensification, the shorter the duration. And we're not 100% sure about more or fewer storms overall, but on balance, the evidence is for fewer but more intense.
So we should have made this webinar an hour and a half so we could get to all the questions. I haven't even gotten to all the questions of Q&A, and I understand there's some in the chat too that I haven't been able to see. I'm going to ask one final question, and then we'll try to see if we can get answers to the questions that weren't answered out to folks afterwards. So apologies that we couldn't get to everything. So here's the final question, Daniel. Kind of looking forward, is there any prediction or forecast models on what we might expect this coming winter season in terms of precipitation and extreme weather events? We've definitely heard talk of La Nina. Do you want to comment on that, what your crystal ball or your scientific crystal ball tells you?
Yeah, I will. And by the way, I don't know if for administrative reasons the webinar has to end right on the hour, but I do have a few extra minutes if we can go a bit longer and answer a few more. But
Okay.
for this question, I think there's a question of seasonal predictability, which ironically is actually harder than looking at the long term because it's what's known as a deterministic prediction. In other words, you need to use the conditions right now to predict the conditions at a specific place and specific point in time in the near future versus using the large scale ambient conditions. What are the greenhouse gas concentrations for general regions for decades in the future? So I'm never, in making these predictions about hydroclimate whiplash decades from now, we're not saying that January 2042 will be extremely wet. We're saying that the likelihood that January 2042 is extremely wet is higher than it would have been in the in the year 1950 or so. This winter, there aren't really strong predictive signals. The thing that we would mainly look to is there likely to be a strong El Nino or, on the other hand, a strong La Nina event? And it was looking like we might be headed for a pretty strong La Nina event. Right now, it still looks like we'll probably see a La Nina event of some magnitude, but that it may not really be all that strong. So unless it becomes sort of into that moderate to strong territory, I don't think it tells us that much about this winter. If it ends up being stronger, then it would probably increase the odds of a drier than average winter in Central and Southern California. At this point, I'm not totally convinced there's a strong enough predictive signal. Now, on the other hand, question about temperature, and unfortunately, there's all sorts of analogies you can use to describe the easiness of predicting above average temperatures now in winter, because nearly every winter temperatures are now above average. So the odds this year, like every other year in the past decade, are that this winter will probably be warmer than the long-term average in California. Harder to say much meaningful about the precipitation at this point.
Okay, let's squeeze in one more question. How do ocean conditions factor in?
So ocean conditions matter for two key reasons, one of which is kind of obvious. The warmer the ocean, the greater the rates of evaporation. So one of the main reasons why atmospheric water vapor content increases potentially in a warming world is partly because the sponginess of the atmosphere, as I mentioned, increases. So its propensity to suck water out of surfaces increases. But of course, in the extreme example of a dry, sandy desert, if there's no water to evaporate, you don't actually experience that increase in evaporation. But of course, one place where we almost always experience that latent potential increase in evaporation is over bodies of water. And therefore, the oceans are the place where the assumption that the amount of evaporation increases with increasing temperature of the water and of the air is almost always true. So years in which the nearshore Pacific Ocean is warmer probably juice up our atmospheric river storms a bit. Because there is literally more water being evaporated from the local ocean that can potentially fall out as precipitation. You still need storms to wring it out in the atmospheric sponge analogy. So just because there's more water in the air does not mean you have more water falling to the ground as precipitation. But statistically, the more water there is available, that when you do get those storms, it squeezes more out. But the other way that the oceans matter is through the fact that different temperature patterns in the ocean, so the spatial variations in ocean temperature, can exert waviness in the atmosphere through concatenation, a Rube Goldberg-like sequence of events. Essentially, it's not just how warm is the ocean, but it is also how warm is the ocean in location A relative to location B. And that is, in fact, the main reason why El Nino and La Nina matter. It's not because they necessarily put more water vapor or less water vapor in the air. It's more because the distant spatial pattern of relative warmth and coolness in the tropical Pacific Ocean affects the global position of the wintertime jet stream in ways that can be semi-predictable. And so it matters both because the actual temperature of the ocean dictates rates of evaporation, but it also matters because the spatial variations in ocean temperatures dictate whether or not we get storms in the first place to wring that water out of the atmosphere.
You are an incredible wealth of information, Dr. Swain. We're going to close it here. I want to thank you so much for joining us today and sharing your experience. We really appreciate you taking the time, and thank everyone for tuning in. We did record this, and we'll send a recording out if you missed anything or want to view something again. We have a second webinar in this series that's scheduled for October 2nd, and that's going to focus on strategies to incentivize groundwater recharge, this idea of letting water spread out and sink into the ground to prepare for future droughts. And that registration page will be live soon, so stay tuned to our emails or follow us on Eventbrite. And if you'd like to follow Sustainable Conservation's work, please find us on social media, subscribe to our email list, or consider a donation. These webinars and our programs are fueled by the generous contributions of organizations and individuals like you. And all new and increased donations are currently being matched dollar for dollar. So please consider donating by visiting suscon.org/give or by scanning the QR code on your screen. So thank you again, Dr. Swain, and thank you again, everyone, for joining us. And we hope to see you again for our fall series. So have a great rest of your day.
Thank you again.